Hello everyone. In this tutorial, I will explain how to make a RimWorld style tilemap shader in Godot. This tutorial assumes that you have basic shader knowledge, such as understanding how UV coordinates work and basic shader mathematics. If you do not, then I highly advise that you watch some basic shader tutorials before continuing. So first of all, let me explain what the RimWorld style tilemap shader is. The idea behind this kind of shader is that the textures are larger than the tile size. In the current example that you're seeing right now, the textures are 1024 by 1024 pixels, while the tile size is 64 by 64 pixels. So in other words, if you divide 1024 by 64, you will get 16. So the textures are 16 by 16 tiles. So any feature will at most repeat every 16 tiles. So if I stop the scrolling here and zoom in on some of the sand, for instance, you can see the sand has a very distinct ridge features that are repeating every 16 tiles. I can also turn off the blending, so it's a bit easier to see or count the tiles if you wish to do so. So let's just zoom out and resume scrolling. And for a more visual example, we can take a look at this 6x6 tile map. This tile map has two textures that are each 3x3 tiles. So now I'm just going to fill this tile map with some random data. You can see that each cell has been assigned either to texture A or texture B. Now, as we go through the tiles, I will take the X and Y coordinate of the tile and use the modulus operator against the width and the height of the texture. So, for example, if you take this cell 4,3 here, you would take the X coordinate 4, and then you would take the width of texture A in tiles, which is 3. So it will be 4 mod 3, which is 1. And then you would take the Y coordinate 3 and mod it with the height of the texture A, which is 3, which would then be 0. So in other words, we should be using section 1, 0 from texture A in this cell. So now we can just repeat this for the rest of the tile map, and you can see that each texture repeats every 3 cells. If the textures you use are seamless, like in the example in the background, the repetition will be a lot harder to spot. But in this example here, I deliberately used textures that are not seamless, so that's a lot easier to see how the repetition works. So for instance, for a good example, let's take a look at this screenshot from RimWorld. RimWorld uses the same technique, and their textures are also 1024 by 1024 pixels. I'm not certain what their tile size is, but this means that the tiles are repeating after a certain distance. However, because of all the foliage, objects, fire, shadow, debris, characters, trees, and the dirt on the ground and such, all these other things that RimWorld has on top of the tile map, it becomes very, very difficult to spot the repetition of the tiles. So how does this tile map shader compare to the built-in Godot tile map? Let's first go through some of the advantages of this shader. In the example you can see in the background, I've added some scripts so that it chunks the tile map and it can go on forever. Each of the chunks will only use a single draw call. This means that in the example you're seeing right now, if I set the chunk size relatively high, so for instance 512 by 512 tiles, it only needs about 4 textures to be visible at one time to always ensure that you have a smooth scrolling tile map, and it will only use 4 draw calls. The blending algorithm that is used is also really easy to modify. As you saw earlier, I can turn it off and on with a single button press, so it's very easy to strip out of the shader and replace with something else. The shader itself is also relatively flexible. It's quite easy to extend with things like foliage or even animated textures. There will be more about this in the last section of this video. Now let's look at some of the primary disadvantages. The main thing is that This tilemap shader may bloat your GPU memory. Each 1024 by 1024 texture takes roughly 3 megabytes, and the shader supports up to 256 of them. So that means that if you used all of them, you would take 768 megabytes of video memory. The setup of the shader can also be a bit more complex. At least if you want a smooth scrolling map like I have here that can go on forever, you will need to do a bit more calculation to get it to work. But all of that is explained in this video. Enough with the introduction now, let's move on to the actual tutorial. So here's what we will cover in this tutorial. You can also use the YouTube section feature to skip to any part you're interested in. I will not go through what is in each of these sections right now, so feel free to pause the video if you want to read it. So let's start with a quick look through the shader code so you can get a basic understanding of how it works. Here you have the inputs for the shader. They are all described in the code comments, but I will still quickly go over them here. This is just a brief introduction. If you don't understand what they are for, don't worry about it, as we'll go over all the code that uses them later on. The first one, tile size in pixels, determines the grid size. Just changing this variable alone is not enough, as you will also need to scale the image the shader is applied on correctly. We will get back to that later in the important info section. Half tile size in pixels is simply tile size in pixels divided by 2. I just use this so I don't have to calculate it for every pixel. Texture Atlas texture size, that's the size of the textures in your texture atlas. As I mentioned previously in the introduction, the texture size for this example that you see in the background is 1024 pixels. Texture Atlas texture width is the amount of textures per row in your texture atlas. Maximum size of the image you can pass to a shader in Godot is 16,384 pixels. So this should be 16,384 divided by the texture atlas texture size. The map tiles count x and map tiles count y is the size of the map we are rendering. This should be at 2 less than the map data sent in, as we assume there is a border of 1 tile around the map. We do this so that we can blend the corners of the map correctly. The next 3 each have their own section in this video, so I will just briefly introduce them here. Texture Atlas is the atlas texture where all the textures used in a tile map are combined into one. Map Data is a texture that contains the data for the tile map itself. This is all in the red channel of the image. The blend texture is a texture that's used for blending tiles together. And finally, the blend texture tiles tells you how many tiles there are within the blend texture. This is the blend texture divided by the tile size in pixels. Before we look at the main fragment method of the shader, let's take a look at the supporting methods. The first method, getTilePos, calculates the tile the current pixel is in. It does this by taking the UV coordinate and multiplying it by the amount of tiles for each direction. And then it floors the results since we don't want to have a decimal in the tile number. Then we add 1 to this number because of the one wide border we have around the map. GetPixelPos in tile will get the position of the pixel we are currently working on within the current tile. This will be a number from 0 to tile size in pixels minus 1. So for tile size of 64 pixels, this will be a number from 0 to 63. It does this by doing almost the same calculation as getTilePos, multiplying the UV coordinate with the amount of tiles plus 1. Then we multiply this by the pixel tile size, so in the default case 64. And finally, we floor the result of this as we are not interested in partial pixels. After this, we take this position and modulus it with the tile size in pixels. The remainder of this for the position of the pixel in the current tile. So as an example, we have the 6x6 grid again, and we take the UV coordinate 0.23 to 0.75. So if you multiply this out, you will see that the x-axis 0.23 becomes 152, and the y-axis becomes 352. If we mod this, both of these by 64, we end up with the current position within the tile, which is x24, y32. GetTileID fetches the ID of the current tile from the red channel of the map data texture. It's a fairly simple method and probably doesn't need much more explanation. getAtlasPixelPos calculates which pixels to use from the texture atlas based on the current pixel position and which atlas texture we are using. First, it calculates the row column of the texture we want in the texture atlas. Then it uses this to calculate the top left corner pixel of the texture. Next up, it checks how many tiles there are within the texture in each direction. It uses this to calculate the pixel position of the tile we want. Finally, it adds the current pixel position within the tile to this pixel position. So if we resume the example from the previous slides, we have a pixel position of 2432, we have a tile ID of 1, and we are in tile 2.5. The first thing we do is calculate the row and the column. Then we calculate the start position. Then we calculate the start position and the tile repeat. Finally, we mod these values by 64 by the tile size, and then we sum them all together to get the X and the Y position that we want in the texture atlas. Finally, we have the get color for current pixel. It just uses get atlas pixel position to get which pixel position to use, and then it fetches the pixel from the texture atlas. Finally, we get to the fragment part of the shader. This part simply uses the previous method we defined to do its work. The first part of the fragment function fetches all the basic information we need, which tile we are on, which pixel in the tile we are on, what's the ID of this tile, and finally what color is the current pixel of the current tile. If blending is not activated, we simply set the result of this into the color and we're done. If blending is activated, however, we need to sample a few more things. We can reuse a lot of the data we fetched, like the current tile and the current pixel, but we need to fetch some more data as well. We start by figuring out which edges and which corner we are closest to. Then we get the atlas texture tile ID for these surrounding tiles and grab the color for each of them. Finally, we do a very simple modulus calculation to figure out which part of the blend texture we should be using. We then grab the correct pixel from the blend texture and extract each of the color channels from this pixel. These color channels contains the strength of blending for each of the 4 textures as a percentage from 0 to 100. There will be more on this later in the blend texture section of the video. Finally, we blend each color based on the percentages we are supposed to use. And that's it. This is the entire shader code. If you understand the basics of shaders in Godot, then this shouldn't be very difficult to comprehend, as it's mostly just calculating tile and pixel positions and grabbing the corresponding data from textures. Now let's move on to the texture atlas. This image you see now is the texture atlas that is passed into the shader in the current example. It contains all the texture the map uses in a single large texture. The reason we do this is because it's faster for the shader to look up from a single texture rather than from multiple textures. I use C# in this example, but this should be fairly easy to translate to GDScript if you prefer to use that, as the code is fairly simple. First, we get a list of all the textures that we're going to use. The order of this list is important, as you use the index of the texture when passing in map data. The textures used are all 1024 by 1024 pixels, and we simply collect them all during loading and generate the atlas from code. Doing it this way makes it a lot easier to replace a single texture or to add more textures. Second, it calculates the width and the height of the atlas based on how many textures we got, and then it creates a new image of that size and locks it. Here you can see the loop that does the actual copying. It grabs the data of the next texture in the list, copies it to the atlas texture using the blendRect method on the image, and finally it just updates the position we are in on the image. We have 16 textures per row, so every 16 textures we go to the next row. Lastly, we unlock the image and use it to create the texture. Now let's have a look at the blend texture. So this is what the blend texture looks like. As you saw in the shader code overview earlier, we use the different color channels of the blend texture to decide how we blend between tiles. I've used a very simple algorithm to create the blend texture as you see here. It's a fairly smooth blend with a little bit of noise added to it. I will now separate out the different color channels of the image so you can better see how the blending works. Here is the red channel. It is used to do horizontal blending between tiles. The way to read this image is that the brighter any part of a cell is, the more of the neighboring cell color is used in that spot. The green channel is for vertical blending between tiles. The blue channel is for the corner blending. And finally, the alpha channel is used for the current tile. How you generate this texture is up to you. The method I use results in a fairly uniform blend with a little bit of noise. Looking at the code here, the method has a few inputs. The smooth edge and smooth corner decides how many pixels away from the edge we should blend. A large number leads to a smoother and wider blend. The edge percentage and corner percentage decides the maximum percentage of blending. So an edge percentage of 50 means that right at the border between tiles we are using 50% of the current tile and 50% of the neighboring tile. As we approach the corner of the tile, we need to blend all 4 tiles together. The current tile, horizontal tile, vertical tile, and the corner tile. As such, the corner percentage is set to 25, so that way we use 25% current tile, 25% vertical, 25% horizontal, and 25% corner tile when blending. The final parameter that's relevant is the texture size. This decides how many tiles we should create. This should be a power of 2, and I recommend setting it to the same size as your textures. It's set to 16 here, since our tile size is 64 pixels, so 16 times 64 is equal to 1024. This makes this blending texture the same size as our ground texture. Now looking at the actual code. The first thing we do is grab 3 noise textures, one for each of the directions, so one for horizontal, one for vertical, and one for the corners. The most important part of the noise generation is that the noise texture is seamless and the size tiles perfectly inside the blend texture you want to make. In this example, I set it to 1024, but I could also have set it to 512 or 256, but that would cause more repetition of the noise. Just like the texture atlas, we create an image and lock it. Then we start a loop to loop through every tile and every pixel within the tile. So row and column tells you which tile we are currently in, and X and Y tells you the pixel within that tile. The actual creation of the texture is slightly more complex, but not that difficult. First, we calculate the actual position within the image. Then we find the closest edges and calculate the distance to the closest surrounding tiles. After that, we simply calculate the percentage based on our edge percentage, corner percentage, and the max smoothing distance, smooth edge and smooth corner. If we stopped here, we would end up with a very smooth and uniform blend, which is why the next step is to add some noise. When grabbing the noise values, I reduce the effect of the noise the closer you are to the edge. The reason for this is that if this is not done, sometimes the noise would completely remove the blending and you would get hard edges. We then apply the noise to the percentage values we have, and finally we subtract the corner percentages from the side percentages. The reason we do this is to ensure smooth blending of corners. If you imagine we are looking at the corner pixel, then the corner percentage would be at max, which would be 25%. But the edge percentages would also be at max, 50%. Add that together and you get 125%, which we do not want. So by subtracting the corner percentage from the side blending percentages, we get a smooth blending. If you don't understand how this works, feel free to download this project and simply comment out parts of this code or change stuff around. Since the texture is regenerated on the startup, you can try out different blend strategies. Final step of calculation is to figure out the percentage for the current tile. This will simply be 100% minus the other percentages. This way we always end up with 100% blend in total between the 4 tiles we are blending. Then we write these values into each of the color channels of the image, and once the loop is done, we simply create a texture from the image again like we did for the texture atlas. The final texture we need to generate is the actual data for our world map. This texture will contain the index for the atlas texture to use for each tile we are rendering. As we currently only need one index, we just put this data into the red channel of the image. If you had more data, such as foliage or animations, you could put that into the other color channels of this image. The code for this is relatively short. We simply loop through the section of the map we are generating, take the tile index and put it into the image data. You will notice that the way this image is created is slightly different from the method used for the blend texture. Here we create a data array and create the image from the data array. This method of making an image is slightly faster than setting each pixel individually, but also adds a little bit of complexity. I do this here since this code is not run during loading time like the blend texture or the atlas texture, but rather run as you scroll around the map, so speed is more important here. If you look at the example project, you will see that the shader consists of three main classes. In this section, I will give a quick overview of what each of these are for. The map shader display could be seen as the brains of the scrolling tile map. At regular intervals, it asks the camera which section of the map is visible. It will then spawn in a map shader chunk to draw this section if necessary. It also keeps track of which sections are currently active and keeps a list of map shader chunks that are inactive. This way it can reuse any map shader chunk that is no longer needed. The most complex code here is a calculation used to figure out which segments to render based on the camera position. Except for that, most of the code is quite simple. The map shader data provider is a very simple class that allows for events, or signals if you're using GDScripts, to be passed between map shader display and the map shader chunk. If you look at the C# code and don't know what an event is, it's essentially almost the same as a Godot signal. If you want to reuse this code as is, then the main thing you would need to change in the data provider is the getTile method, which you can see on the right here. The getTile method in this example code is an extremely simple map generation code that uses a noise texture and just picks different texture based on the value of the current pixel. The map shader chunk is a script that runs the scene that contains the tile map shader. Its job is to generate the map texture, position itself in the correct position, and set all the shaded parameter values. The most complex part of this class is probably the map texture generation, which was already covered in the last section of this video. Next up, we will have a brief look at the two non-shader related classes I included in the demo project. As this shader is coming from my game project, I simply copied these two classes as well, as it was easier than implementing them again. The player camera is a simple camera class for smooth scrolling and zooming. It has some functionality for figuring out its position on a tile map and can be reused without any problem. Feel free to use it for your own project if you need a camera class. Simply attach it to a camera 2D and it's good to go. Just note that it's set up so that it should only be one player camera at a time. If you wish to have more controllable cameras in your scene, then this class will need some modifications. The intPair class is essentially the same as a vector2 in Godot, except that it works with integers. If you want to reuse it, feel free. You will only need to remove the toGlobalPosition method, as this contains a reference to GameManager.TileSize. Except for that reference, the class is completely standalone and can be reused. If you decide to reuse the shader, there are a few important things you should know. First of all, you have to turn on local to scene on the shader if you plan on having more than one instance of it. Else you'll have unpredictable results when you pass in your map data. If you wish to use more than one copy of the shader, then you should turn on GPU Pixel Snap in your project settings. If you do not, you will notice that you will get a border between the different map chunks. This has been mentioned previously, but it's very important that the size of the sprite the shader is applied to matches the region the shader is supposed to render. The Godot icon is 64 by 64 pixels. So since the tile size in this example is 64 by 64, I simply use that. If you wish to change the tile size, I would recommend just replacing the Godot image with an image that matches your tile size. That way the scaling code will still work. Of course, if you prefer, you can also go adjust the scaling code instead. Now, if you wish to simply copy the shader to a new project, that is not so difficult. Start by copying all the C# scripts in the scripts folder and the shader in the shaders folder. Then you just need to replicate the two main scenes. The main scene should contain a node with the map shader display script on it and the camera with the player camera script on it. The second scene should be a scene with the map shader chunk as a script on the root node, and it should contain a single sprite with a shader applied to it. Finally, update the path to the map shader chunk scene inside the map shader display script. If you understood how this shader worked, then adding foliage should be pretty trivial. Simply make a foliage atlas that is similar to the texture atlas, and then pass in which image from this foliage atlas to use in one of the remaining color channels of the map data. A similar shader to this that could be made easily is a fog of war shader. You can make a shader that renders every pixel as black, or use a repeating fog-like image. Then just pass a value between 0 and 1 that sets the alpha value for each pixel through the map data. You could reuse the same blending method as here, just only apply it to the alpha channel. If you made it all the way here, then thanks for watching. If you have any questions, you can find a link to my Discord in the video description. Feel free to drop by and ask if you have any troubles getting the shader to work.